Hello, everyone. Today's lecture is about waves. We're starting a new topic from chapter 13. In this topic, we will be covering periodic signals, which are simple harmonic motion. We will look at definitions of the waves, like the period, the frequency, the wavelength, the wave number, the angular frequency, and then we will look and evaluate how is the wave is being generated, and we will also introduce the two types of waves that we have, the longitudinal and the transverse waves. Waves in general are generated due to oscillations. Oscillations happens. Those oscillations cause the energy to be transferred from one point in the medium to another. So we have, for example, light waves. Those light waves are from electromagnetic types, where here we have the oscillations happening in the electric field and the magnetic field. We also have the sound waves, which are different types of waves. Those ones are longitudinal waves, as we will see later on, where the motion, the vibration is happening along the direction of propagation, while in the electromagnetic waves, the vibration or the oscillation is happening in a transverse way, perpendicular to the direction of propagation. So here it's perpendicular, here the motion is longitudinal, which is along the direction of propagation. For example, if you drop a rock in a pond, you will see that due to the impact of the rock in the pond, the water at the point of impact will oscillate, will go up and down. This kind of oscillation will cause this oscillation to propagate in all directions. And now you will see the motion of transverse vibration will happening in all direction here, as you see, and that's how this wave is being propagated from the point of impact to everywhere in that pond. So those periodic harmonic motion happen uh, in a repetitive way, such that the signal repeats itself every one cycle. So if we look at simple harmonic motion as one of those periodic, that's a special case where basically the driving force depends on the displacement from equilibrium. As we will see in the next example here, if you press this mass that is connected to the spring, then you have created a restored energy, and this spring will result into, when you release it, in a force in this direction pushing that mass till it passes the equilibrium and then extend further. And then this is going to cause a force will be applied in the opposite direction, and this force will result into stopping this mass and then bringing it back in this direction toward the point of equilibrium. If we assume that this point here is the point of equilibrium, so you have always this motion happening such that it goes back and forth. If we assume a zero friction, it will be oscillating forever, such that the distance here is always the same as this distance. So this is the definition of the simple harmonic motion. Now, this signal, this periodic signal, repeats itself every one period that we call it t. So t is the period. Or if I take the inverse of that period, I will get the frequency. How many cycles per unit time this signal is repeating itself. This is the summary of what I have just mentioned about the simple harmonic motion. in this slide. Then if we move on to a periodic signal that we said the simple harmonic motion is one of them, which basically is going to give you a clean periodic function that we can represent mathematically with a sinusoidal signal. One of the features in that sinusoidal signal that it repeats itself every period of t. So the t here, or the period here, is between 2 points that are the same, where the signal goes all the way and come back to the same location, same value here. So this can be represented, as you can see, with this sinusoidal signal. So this is x equals to minus a sine omega t, where omega is the angular frequency here, which is radians per second. Omega t is the phase. So we know that this signal repeats itself every period, a period of t, which is also, as a sinusoidal function, has a period of 2 pi. So if you look at this phase in terms of this omega t in terms of phase, then the signal repeats itself every 2 pi. In this case, I can say that this function can be represented as theta that equals to omega t. So let's look at this example. Here we have a mass attached to a spring that is pulled 20 centimeters to the right from equilibrium and released at t equals 0. It makes 20 complete oscillations in 10 seconds. What are the amplitude and period of the resulting cosine function that describes the position of the mass at a function of time? We have here pulled 20 centimeters, so basically 20 centimeter is the amplitude, which is 0.2 meter, right? Because if you go back to here, you will see pulling it to the right 20 centimeter means that this represents the amplitude. Then it did 20 complete oscillations in 10 seconds. What does this mean? This means that its period is t equals to 10 seconds divided by 20, and then t equals to 0.5 seconds. So the answer is 0.2 and t equals to 0.5 seconds. So what is the wave? As we will see later on, how does the wave propagates? We know that the wave does carry energy. Wave does carry energy. Due to what? Due to a disturbance that you caused in the medium. This disturbance that you caused in the medium caused this wave to propagate. How? By introducing a vibration and oscillation. So if you recall in the example we saw in for the rock that was thrown in the pond, the impact of the rock due to the force coming from that rock caused that medium at the point of impact to be pushed down, and then went up again, caused this oscillation, this vibration, later on caused the wave to get generated and to propagate everywhere. We have to be careful that the medium itself, the matter itself, does not move, does not go forward. So what's happening is this vibration is propagating from to adjacent medium, and then this is how the energy is traveling. And those ones can be, this wave can be described by those definitions that we talked about: the wavelength, period, wave speed, and we'll see the wave number and the angular frequency as well. Those waves, they can suffer from deflection, reflection, as we will see later on. What's the reflection going to cause to my wave, and also interference due to this reflection that will cause constructive and destructive region. So we can categorize that induced wave by traveling wave, a wave that we will look at as a wave traveling in one direction. And then if that wave that's traveling in this direction suffered some kind of reflection, those reflected wave are going to interfere with my traveling wave, and sometimes we call it incident wave, reflected wave. They are going to interfere and they're going to create distractions and constructions. And in this case, this is going to generate standing waves. We will also see how does a standing wave look like. We have two common examples: mechanical waves, like the one we saw uh, in the water case, or it's a sound case. And we have the electromagnetic waves that are basically light, radio, microwave, due to the vibration of the electric field and magnetic field. So we can say those are two types. So we mentioned the transverse wave, which basically we said the transverse wave is happening due to the vibration up and down, and the propagation is perpendicular on this vibration. However, the longitudinal wave, which is the wave that we see in the sound, is basically a longitudinal wave because the vibration is happening along the direction of propagation. So here, the transverse is perpendicular along the direction of propagation. However, the longitudinal here is in the same direction of the direction of propagation. You can look at the example here, an example here of a longitudinal and transverse in this attached YouTube video. We said that at any moment, if I am looking at the medium, that this waves is happening, and at any moment, again, we said that the function that describes how is the medium is doing during this time is a sinusoidal function. It will be a sine theta, right? At any moment, it will be along the everywhere in the medium. It will look like a sinusoidal function because it's a periodic function that repeats itself, right? So if we look at several moments, we will see that at this location, the medium here in this location is up. At this location, it is 0. At this location, it is minimum, and so on. So this one is along the x at any moment. What is the mathematical expression that I can use to describe that wave? This wave can be described with this function that depends on the space and on the time. So this is why the function y, that is a function of space and time, has a magnitude, this is the amplitude of my signal, sine 2 pi t over t plus minus x over lambda. So what does this mean? Let's take it step by step. A is the maximum displacement, which is my amplitude in that signal. T, we saw the T is the period in time domain. In time domain, T is the period. The signal repeats itself every T, which is the period. Wavelength is the wavelength of the signal in one period. How much how much is the wavelength of that signal in one period. So lambda is the length of the signal within one period. And then the plus minus here represents the direction of the travel. This wave signal, as you can see, has a plus and minus. The minus here represent a traveling that's happening along the positive x direction, the minus. If the wave function has a plus, this means actually, so here the propagation is happening in this direction. If my wave signal has a plus, then the propagation is happening in the negative direction. So this is one of the features for the traveling waves. So mathematically, this 2 pi over t, 2 pi times 1 over t, 2 pi over t is actually the angular frequency, which is also 2 pi f. 2 pi over lambda is what we call the wave number, k, radians per meter. So if I am to rearrange, then my wave function, that is a function of space and time, now can be written as a sine omega t plus minus kx, where minus means that my traveling wave is going in the positive direction of x. If it's positive, then my traveling wave is traveling along the negative direction of x. It will be negative. Okay, so here, if it's negative, if this negative, then it will go in the positive direction. If it's positive, then it will go in the negative direction. Okay, so let's go and look at how is that wave traveling in space and time. In order to understand how does the wave propagate in the medium, let's look uh, at the wave given as y equals to xt equals to a sine omega t minus kx. In this case, I'm looking at the traveling wave that is traveling along the positive direction. This is v is the wave velocity. Uh, so let's see how do we draw this wave when it propagates and medium as a function of time and the space. So let's assume that this is the x, y. This is that's my medium, and then I will take at the beginning t equals to 0. I will be looking at several time moments along all over the medium. So let me start first with the t equals to 0. So what's going to happen? Look, assume that I have frozen the time and I'm looking at pace everywhere at t equals to 0. So in this case, my function becomes y equals to a sine 0 minus kx, or y equals to minus a sine kx. Now we know that kx is the wave number. We talked about that, and it is 2 pi divided by lambda. So I have y equals minus a sine 2 pi over lambda x. Now here, I'm still at moment 0. Now I will be looking at several points during this moment 0. So in this case, I will be looking at the 0, lambda over 4, lambda over 2, 3 lambda over 4, and lambda. Remember, this periodic function repeats itself in space every lambda. So it's enough for me to look at one lambda to have a complete idea about how the signal is behaving. So now within this t equals to 0, I will be looking, as I said, at those points, those locations. So let me start first with x equals to 0. For x equals to 0, I have y equals to 0 as well. So this is my first point. Y sine 0 is 0. Then the next point is x equals to lambda over 4. In this case, y equals to minus a sine 2 pi over lambda times lambda over 4. Lambda will cancel, 2 with the 4, and then I have y equals to minus a sine pi over 2. Pi over 2 is 1, so and the answer is minus a. So I know at x equals lambda over 4, if this is my minus a and this is my a, then for lambda over 4, I have my point here. What happens at lambda over 2? So when x equals to lambda over 2, I have y equals to minus a sine 2 pi over lambda times lambda over 2. Lambda will cancel, 2 with the 2, and then I have pi. Sine pi is 0, right? So I have sine pi is 0, and then at lambda over 2, this becomes 0. Then y is 0. Then now what happens at x equals to 3 lambda over 4, y is minus a sine 2 pi over lambda times 3 lambda over 4. Lambda with lambda, 2 with 4 is 3 pi over 2. 3 pi over 2 is minus 1 times minus a becomes a. And again, if you do x for lambda, you're going to get y equals to 0 again. And now this one will be 0. So if I am now to draw this function, it will look like this. That's a sinusoidal function, and this is really a minus sine function. And this is a minus sine function, exactly what I was expecting. Right? This is minus a, and this is a. Now, if I do the same, however, I'm done with t equals 0. Now let me go to the next moment, which is t equals to t over 4. If I do this for t over 4, and then my function becomes a sine omega t. Remember, omega t is 2 pi over, omega is 2 pi over t times t, and here t is t over 4 minus kx. then y is a sine t is going to cancel with 4 pi over 2 minus k x. Now, this is my new function. If I look at the locations from x equals 0 through x equals lambda, so x equals lambda over 4, x equals lambda over 2, x equals 3 lambda over 4, the same thing of what I have done here, and draw the function. I will find that this function is going to look like this. Let me do the first one. So here x equals to 0, which means y equals to a sine pi over 2 minus 0, which is a, right? So now this one for 0, it becomes a. Now if you continue for x equals to lambda over 4, you will find that y equals 2 will give you 0. And then if you continue, then you will find that at lambda over 2, it becomes minus a, 0, and a. Try them, but this is what you're going to get. So if I am now to draw the function, so this is the function that I'm going to get. So this one for t equals 0, this one for t equals t over 4. Now, if I am to do the t equals t over 8, I will be getting another function something like this. Something like this. So this one, t equals to t over 8. So what does this mean? This means if you are to look at the point, this point at t equals 0, you will see that at t equals 4, at t equals t over 8, this point moved, became here, and then at t equals t over 4, moved, became in this point, which means if you run the time, you will see that this point is going to propagate in this direction, in the positive x direction, right? If you run the time, you will see that this point is going to propagate in the positive direction. This is at several locations. Now, if you look at one location, let me assume that I'm looking here at this location. See what's going to happen. This point at t equals 0 was here, and then at t equals to t over 8, it went down to this point, and now at t equals to t over 4, it moved down to this point. So in other words, what's going to happen, you will see that at any point along this x-axis, you will see that the point will be vibrating or oscillating like this along this line. Okay, so at this location, you will see that point is vibrating, oscillating up and down along this line, because this point defines a distinguished location in the medium. Okay, so that's what we were explaining. Then time and distance. Time and distance, what does it mean? How are they related? Time and distance, they're related to velocity. So if I have a signal that is traveling, let's say in x direction, that's why I put the velocity, traveling in the positive x direction, specific amount of displacement with a specific amount of time, then I can get the speed of this wave. So the velocity of the wave would be equals to this specific distance in this specific time. So it is lambda divided by the period, the wavelength divided by the period is going to give me the velocity. Now, what is the period and frequency? It is 1 over the frequency. So if you substitute 1 over t with f, you get a second expression for the velocity, which is basically f times lambda. So in any wave signal, any traveling wave, I can define this wave if I know the wave number, if I know the angular frequency, the period, of course, and the velocity. And of course, how is the wave traveling? Is it traveling in the positive direction or in the negative direction? If I know the wave number k and the angular frequency omega, can I determine the speed of the wave? Can I? I know that the wave number is 2 pi over lambda. So lambda here is the distance. I know that the angular frequency is 2 pi over t. T is the period, which is the time here, right? So in this case, if I divide omega by k, what do I get? 2 pi over t divided by 2 pi over lambda. This is going to give me lambda over t, and this is the velocity. So I know that the velocity v equals to omega divided by k. An example, a wave moves along a string in the positive x direction with a speed of 8 meter per second, frequency of 4 hertz, and an amplitude of 0.05 meter. What are wavelength, the wave number, period, angular frequency, and describe the displacement and y of the particles that propagates this wave as a function of position x and time. So we know that this wave is traveling in the positive direction. So in this case, the wave is going to look, the wave is going to be described as y equals to a sine omega t minus k x direction. I need the wavelength. If I know that the speed is 8 meter per second, I know the frequency for hertz, and I know the amplitude a equals to 0.05 meter. A, the wavelength lambda. If I know the frequency, then I know t, right? Or I can say that the speed equals to lambda times f, and in this case, lambda is v divided by f. Lambda is 8 divided by 4. Lambda is 2 meter. Lambda is 2 meter. The next one would be the wave number. The wave number k equals to 2 pi over lambda, which means k equals to 2 pi divided by 2, and k equals to pi radians per meter. B, C, the period, T is 1 over F, which is 1 over 4. T is 0.25 seconds. Angular frequency, omega, is 2 pi F. Omega is 2 pi times 4. Omega is 8 pi radians per second. E, xt equals to 0.05 sine 8 pi t minus, this is very important because this one is the one that is defining the direction of the traveling wave. K is pi x, and the answer is meter.